Hello everyone. So in the next few lectures, we'll be looking at implementing GPU algorithms. Here we have two parts to this. So the first part is thinking about GPU algorithms because they are quite different from the CPU based algorithms because the mental model has to be shifted from loops into parallel processing. And for thinking about it, we'll be using the work of Ken Iverson. He has got a Turing Award for basically giving us a way to think using notations. And we'll be using his the last programming language he developed, which is J. It's the paradigm that J uses is array programming, which is the exact mental picture that we need for thinking about GPU algorithms. And when it comes to actually implementing the algorithm, we'll be using Mojo. So Mojo was created by Chris Latner. So if you don't know him, he's basically a legend. And Mojo works on AMD, Nvidia, Apple, M series, or any kind of new accelerators that keep coming out. For now, we'll just be concentrating about GPUs, but Mojo is here to stay. And J and Mojo serve different but complementary purposes in this tutorial series. We use J as a language for thinking. Its array programming paradigm encourages us to express algorithms in terms of whole array transformations, making it a powerful notation for exploring GPU style computations. So when it comes to its array nature is what we'll be using it for. We then implement the same ideas in Mojo. Alright, so with that short introduction, we can get on to the series. So before getting on with programming in J, we have to understand how to define a method in J. So there are multiple forms of defining the method. So an adverb, a conjunction, a verb, the add-only verb, and a tacit verb. I'll be posting these notes in the link. You can go through it. Let's first look at what a dot product is. So don't worry about some notations we are using here. We will eventually figure out how to play with this language. So integers up to 8, let's say that's A, and B, let's say it's integers up to 8 again. Let me show you what A and B looks like now. So now the dot product is basically the multiplication of individual elements and summing it up. So the multiplication. So this is what I mean by array programming. You don't see any loops here. Everything is a vector, and as we go through this tutorial series, we will eventually figure out how this paradigm works. And now the dot product is basically just the sum of C. So for that, so that's the dot product. We have a picture of what a dot product is, but when we're trying to implement in this in GPUs, it's basically forms a kernel, and the matrix multiplication kernels are just used in models like GPT, or 80% of these models are just matrix multiplication. So we have to think of them in a particular way to actually implement it in Mojo. So let me try to implement it in one way. Don't worry too much about the details. Once we get onto the Mojo side of things, you will see why we are doing certain things in certain way. Okay, so now we know A and B already. Now we have to make a function for reduction. So the reduction step is going to be, so a function in J is called as a verb, and this verb, because we are defining it with 4 and 0, it takes arguments on the left and right side. You can look at more details in the notes that I have provided in the link of how to define a function or a verb. Okay, so stride equals x. So this is the left hand side argument, which we are calling as stride, and always the left hand side is picked using x variable. So that's a language specific thing. And shared. Don't ask me why we are using these names. You will have to see the Mojo side to understand why we are using these names. It's regarding how certain GPUs function. So we have stride and shared, and active is I dot stride. So you know what I does? It just puts out all these numbers from up to 8, starting from 0. So whatever we give on the left hand side of this function, it just puts up till there, and that's the active. And sums. Okay, active shared active plus stride shared. So this is a new notation. So let's see what that does. It's basically indexing. So to give you an example, let's say 0, 1, 2, indexing 4, 5, 7, 8, 9, 10. So this indexed the 0, 1, 2 indexes of this whole array. So active indexes the shared, which means on the right hand side. Whatever array is put forward, we are just indexing the active indexes of that. And then we are adding up active plus stride, so the left hand variable. Let's see what happens when we are, let's say 0, 1, 2 is the active, and what happens when we add stride. So it becomes 3, 4, 5. So this is taking the So here we have an array with 8 elements in them. So let's say if we have the first active as 4, so in the sums it's taking the first 4, and then active plus stride is basically 0, 1, 2, 3. If we have an active of 4, this is what it will be looking like, plus 4. So 4, 5, 6, 7. So it's basically summing up the first 4 with the last 4. That is what sums is. And sums active amend, that notation is called as amend shared. So let's take an example of what it does. Let's say sums are nine, 10, 11, 12. And active is for, let's say it's 4. So what happens, let's say the stride is 4, so I dot 4 would be active. So the active would be 1, 2, 3, 4, and amend shared, so 0, 1, 2, 3, 3, 4, 5, 6, 7. Oh, sorry. It starts from 0. Okay. So basically what this is telling is to look at these indexes in shared, and change just these indexes with these ones. So change the active indexes of shared using sums. So that's all. So that's the method. And we can I can show you how this works basically. Let's say the stage 0 is A into B. Reduction stages. As I said, why we are doing this, you will figure out once we start using Mojo, because we have to program GPUs in a certain way. Okay, so stage 1 is 4 reduction step stage 0. So 4 is the left hand side, and stage 0, which is A into B. A into B, we saw what is A into B. 0, 1, 4, 9, 16, 25, 36, 49. So 4 reduction step, this array is the stage 1. Don't confuse it with this definition, okay? This is just a way to say that this verb or this method has both left and right parameters. Okay, so that's stage 1. Stage 2 is 2 reduction step stage 1 stage 3 equals 1 reduction step stage 2. Now let's put every shared memory state into one matrix. Every shared memory state into one matrix. Okay, so the states are as follows: 4 8. So the matrix has 4 rows and 8 columns. That is the shape of it, and we are reshaping the following into a matrix of 4 rows and 8 columns. Stage 0, stage 1, stage 2, stage 3. So we are reshaping these values into a matrix of this. I mean, you have to see what stage. So stage 0, you know what it looks like. Stage 1 is basically this. I mean, the numbers are wrong, but anyways, let me just show you what it looks like. Stage. Oops. Oh, I forgot the closing bracket. Once the function ends, we have to use a closing bracket. Stage 2. Oops. Spelling mistakes. Okay. So stage 0 is as we expected. Stage 1, we are summing it up, and we are basically amending the sums in the active indexes of shared. So 16, 26, 40, 58, and the rest of it remains the same. And next time we are doing the same thing, but here the active is 2, so just these 2 things get changed, and the next time the stride is just 1. And here, so in J, always everything works from right to left, so stage 0, stage 1, stage 2, stage 3 were just rows of, were just arrays with 8 elements in them. So we are reshaping using this notation. We are reshaping those 4 arrays into a matrix of 4 rows and 8 columns. Okay, so we have the algorithm now. Now we have a mental picture of how to implement this in Mojo. Mojo is where we'll be looking at how different memories work and how a shared memory works and why we have named this shared and everything. So since I thought going in a sequence would be a better thing, so I know that few of these things are still not making much sense, but you'll see why we did things in this way after seeing the Mojo code. So this dot product implementation is being picked up from uh, modular puzzles that they have released to teach Mojo. So we'll be using the same thing, and since we already have a mental picture of how from the array based J how this parallel programming works to some extent, let's implement it in Mojo. Now Mojo has compile time parameters. So threads per block. So a GPU is divided into multiple blocks and grids and threads. You can learn further about what a block is, what a thread, what a grid is by looking at the documentation that Modular has provided, or even from NVIDIA or anything else that you find on the internet. It's pretty much available to show you how the architecture of GPUs are. So here the thread per block is 8. Size of the array we are using is 8. So from J we saw that the array size was 8. Blocks per grid. So grid is a 3-dimensional unit, and so here we have one block in the grid because the size is just 8. Threads per block. Okay, it's in each block the number of threads is 8. The one is just customary, so there's nothing in the Y direction. It's in the X direction. Data type is also something we pick when compilation happens. So data type dot float 32. And the layout is row major size equals row major 1. So the output is just one element. That's why it's a row major, which means the computation happens in a row way, like 1 2 3 4, not in column 1 2 3 4. So it happens horizontally. Okay. Out layout, and the layout type of layout, and Okay, so we got everything to get started. Let's define the dot product now. Keep the mental picture that we developed with J in your head. Output is, so tile tensor is a very convenient way of mapping where things fit in the memory. So without this, we would have to do a lot of manual handling of data. I will link an article that you can read to further understand what tile tensor does. So, but for now, we don't have to look into the nitty-gritty details of how it works. Just use it. So output is something which can mutate, and the data type is float. So and A is again the same thing. Let me just copy this. But the layout type is different. Layout type. Size tab is int 32. Okay. That's what the size looks like. Because of how the memory is allocated, the shared variable is something that each block shares. So the movement of memory happens quite fast in this, and is accessible for each thread in a block. That's the reason we are using shared. So stack location type equals data type address space equals address space dot shared. Row major, that's per block. Okay, so that's how we are defining the shared, which is a stack allocation with these parameters, and the address space is a shared address space, which means it's available to all the threads in a block. Okay, now let's define global I. It's block dimension x into block index x plus thread index x. local I equals thread index x. Okay, global I and local I. Global I is the index that we can map to any thread in any block, and local I is a index that is block specific. So we are using block local I for the shared stack and global I for A and B. So let's see. Now let's do the element wise multiplication. Let's do the element wise multiplication first. Multiplication first. So if global I is less than size, global I is less than size, which means that we already have the size of an array, and if our global I exceeds that, we don't need the value from those threads. So it's going to be shared local I A global I into B global I. So I know that you might be confused with how this global I, local I, and all these things are working. So in the notes that I have provided, and the explanation bit that I have provided, you can see further into how why it's global I and why global I is this, and why we are using local I for shared. So I understand it's going to be difficult initially, but you can go through the notes and do some research and get to it. Global I. Okay, so we have that going, and then we don't want because we are not looping things, there is a chance that we pass on the data before actually all the threads get settled down after the computation happens. So we had to create a barrier before we pursue further, so that all the computations in the threads happen, and then we move on to the next step. So we have to, this is basically a synchronization step. Step. Okay, now parallel reduction and shared memory. So in J we implemented this in a particular way. Here let's see how it works. Reduction. So stride is equal to threads per block divided by 2. So while stride is greater than 0, if local I is less than stride, shared local I is equal to shared local I plus stride. So do you get the connection? Stride local I local I plus stride. So you remember from our J code how we did this. So it's the same mental picture for it. Barrier again to synchronize the threads. Stride by 2. So this loop, I said we are not using loops for tensors, but this is a different kind of a thing, right? So here the multiplication is happening across all the threads inside the size, and here the summing up is happening across the threads of a particular stride. So the initial stride would be 4, and then it gets divided by 2, so it's 2 and then 1. So you should look more into what is the difference between this looping and what is the difference between parallelly doing these things. Okay, so now if local I equals 0, we're just taking the first index value, because after doing these steps the dot product sum would be in the first index of the output. Output 0 equals shared, first output of the shared. Okay, so we have our kernel here. Let's try to run this.